Today, we're going to talk about generative models, which is basically one AI applications where we can generate realistic photos like this. Isn't that amazing? This is basically the evolution of this research topic. Going from 2014, we can barely generate, some recognizable faces, and then we start, have a little bit more details, right? And then fast forward, just 3 years later, you got this photo. You're like, if I don't tell you this is a generated person, you won't be able to tell, right? I don't think you're going to be able to tell this is actually computer generated data. Do you guys know what can we do with this? If we can generate any examples and the computer can generate some realistic images, right? What can we do with this?
It limits the need for social media influencers. When companies want to do product sponsored posts, they usually ask influencers to pose with a certain product. And instead of having a real person do that and spend money on that, they can have a fake.
So you can have fake social media influencer, and you have fake fans. We're going to a rabbit hole pretty fast. Okay. All right. That would be one case. What else, Ramona?
I was thinking on a similar note, maybe that's the model, they wouldn't need as many models. They could just generate look the perfect features to match their clothing. I don't know.
That too, right? You can generate models. And by the way, guys, this doesn't have to for generating realistic faces. This is literally you give a class of things, it can generate anything. So for example, one of the most interesting applications I think would be in video games. Because have you guys seen these crazy kind of video games settings for example Call of Duty? So Call of Duty is this first person shooting game, for example people like that. But you also have very realistic environment like this. Now the big studios, they spend big money, right, to create environment like this, because every single vehicle, every single building, they're drew by an army of artists, right, using computer software, of course. But AI can essentially drastically reduce how much, for example, to produce a vehicle like this. Used to be, if you just create a vehicle like this, it's actually a few $1,000s in the virtual world. But what if you have AI can generate these details, right? And you just need artists a few clicks to select the best ones, right? So generating models has ability to do that. And if you can generate, for example, vehicles and, maybe a trash can, maybe this explosion, maybe that's helicopter, maybe that, building, you can build realistic worlds. And when you can build realistic worlds and you can apply certain simulation rules on top of it, wow, look, you actually have an engine to generate training data for self-driving cars. Oh my gosh. And if you can do that, this means that our training data for self-driving cars is not going to be so expensive anymore. And we can generate thousands of years or millions of years of data, all kinds of different scenarios, cover all the scenarios that's possibly going to happen in the real world. And oh my gosh, that has broad implications. Do you guys see that? It goes from pretty small concept all the way to a world-changing ideas. Let's scale back a little bit, okay? Let's try to stay with the lecture. Yeah, so maybe one of the ways to think about this idea is how do we create models that understand basic features of dogs? Right? That is, if you want to generate some, you have to understand the different features of dogs first. And dog comes with all kinds of varieties. Do you guys know who Richard Feynman is? He's essentially the greatest physicist of our time that essentially gave us more understanding of QED, which is quantum electrodynamics. He famously said this sentence, and we agree very much, that is, what I cannot create, I do not understand. Right? If you want to understand, for example, how different machine learning algorithms were able to detect different features of different breeds of dog, can we maybe make an algorithm? It can create maybe different pictures for different species of dog. Can we do that? And the answer is yes. So you guys are fortunate enough. This class is not happening in 2016. This is happening in 2020, and we have learned how to use generative models for realistic images. So every single image here, every single face here, they are actually generated by machines. And they were quite realistic. They got wrinkles, every single hair is there, right? It's amazing, right? It's amazing. I could not believe it. And you can also use generated models, right, for colorization. That is, you have this Native American picture, and then on the right-hand side, it's actually using machine learning for colorization. And talking about this concept of self-driving cars, let's take a look at this. The whole world here is actually generated.
The frames that you see is not rendered by a graphics engine. It's actually rendered by the AI technology that we built.
This is the first time we combine machine learning and computer graphics to do image generation using deep networks.
For training data, we're given some driving sequences of different cities, and then we use another segmentation network to extract the high-level semantics from these sequences. We have the UE4 engine to generate these colorized high-level layouts. Different objects with given different colors.
The network converts this representation to images.
I made my co-author to dance Gangnam Style, which I don't think he would do by himself.
We find some good dancing videos from another person, and then use my model to synthesize the dance move. That was created by machines. It's not me.
That's pretty amazing stuff, right? It's pretty amazing stuff. Okay, so let's learn, for example, how do we generate images? Have you seen this image before? Image classification, right? We do extract features first. You see all these conv-nets, right? These, max pooling layers. What they do is basically they're extracting the essential features from an image, right? And then the fully connected network, they're combining different features together, right? So that I can make predictions as, if this image is number 4 or, number 5. So image classification, we first extract features. So these are the features that we have, and then can we maybe use it to do something interesting? So, the way to think about this is just that we have these input data, right? Which are basically, these handwritten digits, or it could be rotten food, it could be poisonous, plants, right? It could be anything, right? It could be, things that we need to recycle. The encoder here, which is essentially what I just drew here, like this. There are conv-nets, right? The conv-nets gradually reduce the dimension, right, to smaller and smaller kind of matrices. These are what we call encoders. And we know that these encoders, what they do is basically they condense and summarize different images, their features together into this kind of feature kind of space. And now we're just going to call them encoder. So encoder extract essential features. And then, what we can do is we can do this reversely. So what we do is we put a decoder together. And this decoder, the way to think about it is basically, there are also a bunch of conv-nets, but they're deconv, okay? They go the other direction. So you go from a few features to essentially images. You got it? So once again, you got a bunch of images, you extract the features, you get to the feature kind of map, and then you basically doing deconv and get the images again, So in this case, we basically was able to use the decoder, right, to get some images based on the features. But then how do we train this? Well, the way to do this is you have this input data here, right? This input data is images, and you want essentially these features honestly represent everything about this image. So therefore, the reconstructed input data should be similar to the input data. So therefore, the loss, right, which is something we want to minimize, is equal to image minus this image and square it. Right? So we're just looking at pixel by pixel distance, okay? And try to force essentially these guys that are equal. And what we're training essentially this encoder and decoder so that they would do this job. So the first question, do you think this is supervised or unsupervised machine learning model? What separates a supervised versus unsupervised machine learning model?
So supervised would mean that you provide examples and then and see what it and then you feed in some new data that's unlabeled and see what it does. And then unsupervised, you just like feed it the data and then see what patterns it recognized.
Right. So did we feed in label in this case?
No. So would it be unsupervised?
We fed in data. We never fed in any label. That's right, Ramona. This is actually, unsupervised machine learning model, which is really, really cool because we don't have to label those data. So how do we generate data using a trained autoencoder? What do you think? So again, we have this encoder and decoder. What can we do? Encoder generating data or decoder generating data?
Decoder maybe?
Yeah, decoder is generating data, right? So it's basically, you got this encoder here. Remember, this is like, hundreds of thousands of pictures. They create a feature, set like this. And for every single image, is basically activating different combinations of these features, and then was able to generate realistic data, and that data has to map back here. So what if we just take this whole thing, discard the encoder, right? Forget about that, right? We just take a look at the decoder. That's all we need. So it turns out what we can do, right? It turns out what we can do is we basically have this feature space. And what we do is we sample from the feature space, and you basically generate data from that feature space. So all these notations, they're actually just from probability and statistics, right? So this is basically you sample, this whole thing using some kind of distribution, right? And then given essentially the sampling, right? Given the sampling results, and you generate a mean and a variance, okay? Generate mean and variance. So this is the mean and this is the variance. And then you have this, Gaussian distribution where you have this mean and variance, right? And you're basically picking up data using that probabilistic model, right? So in this case, it's not, for example, you generate Z and then everything is deterministic. That's not the case. What you're actually doing is basically you first generate these mu and sigma, which will give you a distribution. And from that distribution, you will be able to sample data. And the results are, something like this, right? So this is what we call variational autoencoder. And for example, the generated data from variational autoencoder, for example, this is, we're generating the handwritten digits. Here we're generating handwritten digits. You can see here, it was actually, trying to basically, as you're modifying Z, right? You can see how these, data is changed. And here, when you look at Z here, so the Z, maybe one of the Z's would be like, is this person happy or not, right? So you can see here, the person on the top, that person not very happy. And then gradually, as you go down, the person is very happy. And also there's another dimension, which is basically, is the face like centered or tilted on the left or versus right. There's this x-axis, which is basically the head is tilted left or right. And the y-axis, right, is how happy this person is. So you can see here, literally what this thing does is just basically picking up, from that Z parameter. In this case, they're just like, maybe Z is two-dimensional. You pick up, one of those combinations. And then from that one of those combinations, you generate based on that decoder, right? So this is called a variational autoencoder. And you can see here the variational autoencoder, we can use that to generate animated, characters, right? The faces. The pro of variational autoencoder is that they're pretty simple to understand. But the con is that often they generate blurry images, right? Because all these, data points that are sampled from a distribution, this is an active area of research to see how we can generate more realistic, photos. Okay, so that's variational autoencoders. The reason why we wanted to introduce you a variational autoencoder is because it has pretty simple concepts. But the real star of these algorithms are these things called generative adversarial network. We're going to call them GAN. And the intuition, right, is very similar to this kind of game, right? That is, you have cops who are trying to catch you if you counterfeit money. And if, for example, the cops will be able to catch you once you counterfeited some money, and you should learn from your mistake. And maybe you can make better money next time. If you can make, better fake money next time, right? More realistic money. The cops won't be able to catch you next time. That means you win. However, in that case, the cops will be penalized, and the cops have to basically learn from his mistake or her mistakes to see how, they can catch you next time. So the cops will improve. And once the cops actually improved, that means you will suffer. So you have to improve in order for you to make better fake money. You see this cycle here? So it's basically improving one step at a time. I don't know about you guys, but when I was, your age, when I was a junior high or something, I always had an enemy. I always had one. And he's always the best looking person, has the best grades, is most popular. I don't know why I set myself in that kind of situation. And then I always just try to beat him. And we improve together and we become best friends. That's at least my history. And when I think about it, wow, I was applying GAN like in my early age. GAN is actually pretty good. All right, so there are two concepts here. So one is this generator network. It's try to fool the discriminator, right, which are these guys, by generating real looking images. So using this analogy here, is the criminal the generator or the cops the generator? What do you think?
The criminal is the generator.
Yeah, the criminals are the generator. And the cops, they are the discriminator, right? What they're trying to do is they're trying to distinguish what are the fakes versus what are the real images. So you understand the concept now. But in reality, how does this work? Well, so this is sort of like the real, kind of like architecture, really simple architecture drawings of how this thing would work. So you first have some kind of like random kind of sample, right? And use this generator. This generator again, right, is very similar to what we had before. What we had for, basically deconv neural nets, right? Deconv neural nets. So these guys would generate a bunch of images. But if these images, they are fake, right? They're not real. And then you basically take these generated images and you say you label them as 0 because you know that they're fake, right? You label them as 0. And then you have these real data samples, right? So these could be, for example, animated characters, could it be currency? So, you would basically take these currency, maybe they're yuan, maybe they're pound, maybe they're dollars, whatever they are, and you label them as 1 because those guys are real images. And you give it to the discriminator. You give it to the discriminator. The discriminator job, right, very simple, is, you basically have these real images and fake images. Of course, we don't tell the discriminator, right, what they are, right? And we shuffle them, right? So you got this like, basically a bag of images. You give to the discriminator, and discriminator's job is basically be able to tell each image whether that's fake or real. So the discriminator would give those, examples, give those results, whether it's 0 or 1, right? 0 being fake, 1 being real. Now, the kind of interesting things here is that once the discriminator make its prediction, right? Make the prediction. So if I can annotate it here. So you basically have, real label or labels, right? Labels. And that would be, maybe 0, 1, 1, right? 0, 0, 1, 1 here. I think this is pretty simple. And then predictions, right? Predictions, right? Then you have something, maybe it's like, 0, 1, 1, 1, 1, 0, 0. So in this case, right, the description, the predictions, right, is missing a few predictions. So what we can do is just like what we did for training classifications, we can just say, we get these loss here and we train the discriminator. Basically, it's just like the cops are like in training mode, they look at a whole bunch of different currencies and they try to discriminate which are real money, which are fake money. And then right after the training, maybe their sheriff would be reviewing the answer, which are the correct ones, which are the wrong ones. And then the sheriff can train these new cops so that they can do better next time. So during that process, discriminator improved itself. Now the discriminator improved itself, then what we're gonna do is basically we're gonna go back and then we're gonna fine tune the generator so the generator can generate better images, okay? You see that? All right, so let's look at more details, even more details. This is from the original paper of how to train GAN. One of the things you have to realize gradually in life is that once you see intimidating stuff, don't be intimidated. Just stare at it for a long time and gradually it's going to make sense, okay? So, you just have to be persistent. So what we are doing, right, is for the number of training batches or training iterations, for the case steps, we first sample mini batch M noises samples from the noise prior. So this is basically we're trying to generate data. Sample mini batch M examples from data generating distribution. So essentially here, we are generating data. And then you update the discriminator, okay, using stochastic gradient. So what's going on here, if you go on and learn about machine learning a little bit more, you will see this is essentially cross entropy loss. Okay, so that name might be a little bit intimidating, but all this does is basically, the loss in if you have real and fake, and you predict sometimes right, sometimes wrong, right? That loss, when you write it down, the analytic form is something like this. So we're basically, keep on training the discriminator, and then gradually you're going to come back here. Here you're updating the generator. So for each training iteration, right, as I said, you're generating a bunch of data, you update your cross entropy loss, right, updating your discriminator. And once you have done that, the discriminator is never going to change again, right? And then you basically update your generator. So that's in the original paper. So I guess, to make sure you understand it, right? So first you train the discriminator first. You have these guys, you basically have the generator locked, and you basically generate a whole bunch of images. You mix that with the real world images. So this could be cats, factories, motorcycles, whatever you want. And then you give to the discriminator, and the discriminator will predict for every single image, whether that's real or fake. And then from these predictions, as well as the ground truth, you can get the loss. And do you guys remember the back propagation algorithm, right? So that's essentially use the back propagation to update the discriminator. The generator is something, we're going to update next. That is, you fix the discriminator, right? You will come back with loss as well. So discriminator never update again. You basically just keep on generating data, and you can see whether you can actually, fool this guy or not, right? And then you use the loss to back propagate to generate better data so that you can fool the discriminator. You got it? But you can see here, this is, sort of like kind of in the reverse direction. You want this loss to be huge. You want this guy to suffer, right? That's the difference. In the discriminator case, you want the loss to be small, right? You want the loss to be small because you want to basically the prediction, right? And the real label, they're the same. So you want to minimize the loss. Whereas here, you're basically saying, I want to fool this guy. So this guy will do some predictions, but I want this loss to be huge. You see that? That's the difference right there. So if you go back here, you would discover this guy here is actually trying to doing gradient ascent. So here are some results, right? The training data here probably are celebrities. I don't know. Do you guys think this person here vaguely look like Beyonce? I don't know. She vaguely look like Beyonce. We should definitely do I don't know. I felt like I want to do this project where we take all our own pictures, right? Like, we have 15, training people here. Each one contribute maybe 100 pictures, and then we have like 2,000 or 3,000 pictures, and we just generate a whole bunch of people that look like us. Isn't that be fun? And then we send to our friends to be like, hey, we have a secret, sister you never knew about. Please meet her. That'd be a lot of fun, right? Look at that. You can generate realistic bedrooms. We can actually give this person a personality and some kind of life. This person would be, this is what his bedroom looks like, right? You can see here, this is pretty stunning, right? It's like, got these lights, got these different windows, usually got a bed. Sometimes these windows look a little bit weird. I don't know. This window looks a little bit weird. This ceiling looks a little bit weird. But mostly when you don't have, high resolution images, this looks like pretty stunning. Look at that. You can generate various objects, cell phones, bicycles, this horse with weird ears, different horses. Man, I want to do this project so bad. So we might actually create a class around a gun. This could be something we can do maybe next year. We have lots of ideas and we just don't have enough time to work on.